Hello everyone. In previous video we have understood dipole moment of ortho, meta and para dichlorobenzene. In this video we will understand boiling points. Let's first check the values. Ortho dichlorobenzene, the boiling point is 453 Kelvin. Meta case, the boiling point is 446 Kelvin. And para case, the boiling point is 448 Kelvin. Means out of 3, meta have least boiling point and ortho have highest boiling point. Let's try to understand. Boiling point directly depends on intermolecular force of attraction. For example, if I have a liquid A, so this liquid A will made up of AA particles. And between AA particles, a force of attraction will exist, which we call intermolecular force of attraction. Boiling means converting liquid into gas. To convert liquid into gas, we need to break these force of attractions. These intermolecular force of attractions we want to break. That's why we are applying heat energy. Now, how much heat energy will be given by us? It depends on force of attraction. Strong force of attraction, more heat is required to break it. More heat, more boiling point. Weak force of attraction, less heat you require to break it. Less heat, less boiling point. Means the boiling points of a liquid is directly decided by intermolecular force of attractions. Now the case which we are dealing, ortho, meta and para dichlorobenzene, which force of attractions are existing between their particles? So intermolecular force of attractions I am writing. Intermolecular force of attraction which are existing between the particles of ortho to ortho, like between, this is first ortho dichlorobenzene, this is second ortho dichlorobenzene particle, this is third ortho dichlorobenzene particle. So which force of attractions are existing, that I am going to write. There are two. Dipole-dipole interactions, and second, van der Waals forces. How dipole-dipole interactions are generating? We know chlorine is negative due to more electronegativity, carbon is positive, same here, chlorine negative, carbon positive, chlorine negative, negative, positive, positive. So negative have attraction with positive and positive have attraction with negative. In this fashion, dipole-dipole interactions are getting generated between these two particles. And how much dipole-dipole interaction will be there? It is decided by overall dipole moment, which we have calculated in previous video. So overall dipole moment is high, so dipole-dipole interactions will be high. Van der Waals forces depend on surface area. So one by one, I will discuss each force and we will try to find out the pattern of boiling point. First, dipole-dipole interaction. This is ortho dichlorobenzene and this is second particle of ortho dichlorobenzene. In previous video, I found the value of overall dipole moment is 2.92 dB. It also have a 2.92 dB. Okay. So side by side I am writing meta so we can compare. Meta particle, meta particle, and also I am going to write para particle and para particle. Okay. So ortho cases, what is the dipole moment? 2.92 dB. Dipole moment values I am writing. How we have calculated these values? Through parallelogram law. Meta case, the dipole moment will be around 1.83 dB, and in para cases the dipole moment value is 0. So if I talk about dipole-dipole interaction between ortho cases, it will be strongest. So 1, 2, 3, 4. 4 lines I am drawing between these two. These 4 lines are representing strong dipole-dipole interaction because the particles have high dipole moment. High dipole moment means overall high charge is there. So that's why force of attractions are also strong. Now when we will move toward meta, you can check dipole moment value is decreased. So at the place of 4 lines, I am going to write only 2 lines. The 2 lines are representing weak dipole-dipole interaction. Whereas in para, actually, I should not write any kind of a dipole moment over there, dipole-dipole interaction over there, because dipole moment values are 0. The overall particle is non-polar. So there will be no dipole-dipole interaction. Now first factor we have checked. Let's check the boiling point now. What was the boiling point of dipole? 453 of ortho case. Meta case boiling point was 446 and para have 448. If I talk about van der Waals forces will be same in all cases because van der Waals forces depend on surface area, means size of the particle, molecular mass. You can check size of the particles are same, 2 chlorine, 1 benzene, 1 benzene. Every case have 2 chlorine, 1 benzene, 2 chlorine, 1 benzene. Van der Waals forces are same. Okay, then check this pattern. What is the boiling point? 453. What is the boiling point? Among all three, we have a highest boiling point of ortho. Why? Because of strongest dipole-dipole interaction. Because these cases have highest dipole moment, means they are highly polar as compared to other particles. Okay, then question arises. Then why meta have 446 Kelvin boiling point and para have 448? Instead of the fact that meta have dipole-dipole interaction and para do not have, so para should have lower boiling point. Why meta have low boiling point as compared to para? Let's try to find out the answer of this question now. I hope we got from why ortho have a highest boiling point, because of strongest force of attraction. But now point is, between meta and para, why para have more boiling point than meta? The reason is symmetry of paramolecule. Symmetry of paramolecules. Out of para and meta cases, para cases are more symmetrical. Due to more symmetrical nature, the particles can go very much close to each other, or you can say they can pack well. How we can check the symmetry? Look, it is very easy to check symmetry. This is para-dichlorobenzene. Draw a mirror. What will be its mirror image? This. Without any rotation, you can superimpose this mirror image on this. Check. Just take it and try to superimpose. Superimpose means chlorine should come on chlorine, every carbon should come on carbon, hydrogen. So in this fashion, every atom will superimpose on each other without any rotation. But if I talk about meta or ortho cases, suppose this is meta and here we have a mirror, so its mirror image will be something like this. Can directly I pick and superimpose it on its mirror image? No. Check. If I will pick it directly and will try to superimpose on it, is it possible? No. To superimpose this mirror image on it, at least I have to rotate it 180 degree. First, I will rotate it like this. After rotation, this chlorine will come here and this chlorine will remain as it is because I am going to rotate it like this. After 180 degree rotation, then I can fit it on its mirror image. So rotation is required here. Rotation is required. How much? 180 degree rotation to superimpose this molecule on its mirror image. And this molecule was getting superimposed on it without rotation. Means this is more symmetrical and this is less symmetrical. That's it. This is the point which is making difference between boiling point of para and meta. Para particles are more symmetrical. Okay, no doubt they don't have a dipole-dipole interaction, but due to more symmetry, they are getting close to each other. They are getting packed well. But between these two particles, meta cases, dipole-dipole interaction is there. Dipole-dipole interaction is there, but packing is not so well because the particles are not symmetrical. But here, dipole-dipole interaction is not there, but particles are symmetrical, so they can pack well. Means you can say symmetry is dominating over dipole-dipole interaction. That's why the boiling points of para cases are more than meta. And if I talk about ortho and para comparison, this is ortho and this is para. So why ortho have more boiling point than para? Here you will say the dipole moment or dipole-dipole interactions are dominating over symmetrical nature of para. Para is symmetrical but don't have a dipole interaction. Ortho is non-symmetrical or you can say less symmetrical, but it have strong dipole-dipole interaction which increase its boiling point too much as compared to para. So these are the reasons we have for for boiling points of ortho, para and meta dichlorobenzene. Thank you very much. In next video, we will understand boiling points of other haloarenes.